Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientist with me, Sue Marchant, and Chris Smith. Right, what's the latest in the world of science?
Well, it's quite an interesting paper that's come out this week from some researchers in France. This is Marc Vicherec and Mathieu Lefebvre, who are researchers at Earth Physics in France. And they've been looking at the age-old question of the dark side of the moon, not the Pink Floyd album, so much as the real moon up in the sky, and the question of, was it always the way round that it is today? Because although we never see the dark side of the moon, and the reason for that is that because the moon is tidally locked to the Earth, the moon is turning ever so slowly and at such a rate that it completes one complete lap of the Earth once a month, and it also turns one complete orbit on its axis once a month. And the consequence of both of those phenomena is that it always points the same face towards us all the time. That's why we have a dark side. But what's very interesting is that these two researchers were analysing the patterns of craters on the surface of the moon. Now, if the moon had always been in the configuration that it's now got, then what you should see is lots of old and more numerous craters on the edge of the moon pointing in the direction of travel, and fewer craters on the backside of the moon, because it's the same as a car driving down a road into a rainstorm. Because the car's driving into the rain, you're going to get more rain spots on the windscreen than on the rear window. But when they analysed a pattern of 46 craters on the surface of the moon, they find actually the relationship is wrong. And although the western edge has more young craters and the eastern edge has older craters, there are more craters on the eastern, trailing half of the moon than on the one at the front. So this is like a car which must have been driving in reverse, or something funny's gone on. And so their theory is that what's happened is that at some point in the moon's history, a huge asteroid probably clobbered the moon, and it actually knocked it off kilter and spun it round. And so for a period of time, the moon would actually have rotated a bit faster. And if you'd been living on Earth during that time, this is a long time ago, well before humans, of course, but you would have seen the moon turning very slowly on its axis. So the man in the moon would have disappeared periodically. And it's only more recently that the moon has adopted its more static configuration now, tidally locked to Earth again. So it's an intriguing hypothesis. Obviously it's going to take a bit more study to prove that, but the maths and the observations certainly add up. So it looks like the moon did turn at once and turn on its own axis, and that the man in the moon would have disappeared once in a while.
Let's start with some questions, Chris. First of all, Steve in Wormingford has called in. Thank you, Steve. He says, the green powder-like substance that you see occasionally on trees, is this caused by acid rain? What is it, Chris?
The green stuff are plants, and plants on Earth have green chemicals called chlorophylls in them, and they are the chemical that locks away sunlight. They take the energy from sunlight, they combine that energy with carbon dioxide and water to make molecules of sugar. That's how plants make energy and in the form of chemical energy from the sun. So anything that's green on a plant or on a tree is almost certainly going to be algae, microscopic plants, and that green pigment is their way of capturing light from the sun. So I think the green stuff you're seeing on trees, unless it's paint in some circumstances, which occasionally people paint trees green, that's going to be a plant, and it's going to be an algae or a species of algae.
Oh, right. So if you were to perhaps, cultivate it in some way, would something else grow?
Well, it's unlikely, because the bark on the tree and the local environment created by the tree gives it a very specific environment in which to grow. So it creates a sort of niche for that algae to grow on the tree. So if you were to change that environment by scraping the algae off, it would be more difficult but not impossible to cultivate it. So you tend to find that algae are quite well adapted to certain environments, and they'll exploit that niche quite well. And you can see the effect of this. If you look at a tree, you might find more algae on one side of the trunk than the other. And that's because there's quite literally a microclimate being created by the tree. There's less light or more light on one side or the other. There's more dampness or dryness on one side than the other. And the right sorts of algae exploit those conditions and grow in optimal conditions.
All right, interesting stuff. Now, and on the phones, Dr. Chris, we have Peter. Good evening, Peter.
Hello there.
What's your question?
My question is, light bulbs are being made redundant and we're being forced into buying low-energy bulbs, which saves the carbon footprint. Low-energy bulbs, as I understand it, contain mercury. There's nothing been set up to dispose of these bulbs. So what are they going to finish up in landfill? And then when they break and percolate into the water table, is the damage going to be worse than the carbon footprint?
It's a good thought, Peter, and it's a hard question to answer because the answer is, I think, here, there's no simple solution. We should explain why they've actually got mercury in these bulbs, and the reason is that, like all fluorescent light bulbs, they use mercury, or like not all, but many fluorescent light bulbs, they use mercury to make the light. The way it works is that you have a gas at low pressure inside the light bulb tube. The gas also contains a few atoms of mercury, and an arc is struck inside the tube, so an electric signal, a wave of ionisation, flows inside the tube, and this excites the mercury atoms, and the electrons orbiting the mercury atoms get booted up to slightly higher energy levels. They then fall back to their starting energy levels, but in the process they give out some energy at the ultraviolet wavelength. This then hits the surface coating on the glass of the tube, exciting this covering, which is called a phosphor, and the phosphor then glows, producing that nice warm white light that we like, or not like, in the case of some energy-saving light bulbs. So the mercury is useful, but it is present only at very low levels, thankfully. And it's not really that different from all the other strip lights that we use. And I think probably it's which is the worst of two evils. Do we want to have big carbon footprint, lots of fossil fuels being burned because we're turning most of the energy coming out of a light bulb into heat? In other words, about 5 times to 10 times more energy coming out of the light bulb is in the form of heat than usable light. Or do we want to have a small carbon footprint and use a little bit of mercury? I think the environmental equation finds in favour of the latter, which is that it's better to have a little bit of mercury in these things than to make a big carbon footprint.
I lived in Germany. You couldn't even chuck a battery away in Germany. It's against the law.
I think that's coming in here, isn't it? Because we're being discouraged increasingly to throw things like batteries away. People are being told that more and more of these things should go to specific repositories because people now accept that a lot of these things have chemicals in them that A, can be recycled for a start, that are expensive to get in the first place, and B, there is a contamination risk. So I think it's all about being responsible, really. And as we move forward on this, I think probably we will end up with a stage where we are able to recycle more and more things, and also not just recycle things, but dispose of things more responsibly. But the thing that's held this up so far is that if you do the calculations and you say, OK, we're going to have a special bin for energy-saving light bulbs, you then got to factor into the equation that someone's got to empty that bin, and that costs money. Someone's got to bring probably a lorry to come and collect that, and that will burn fuel, and that will make carbon dioxide. And if you add all these things in, before you know it, you've actually been worse for the environment than if you'd stuck with a 100-watt incandescent bulb.
Well,
so it's a difficult one to answer, isn't it?
Peter, thank you so much for your question.
OK,
Take care. Bye-bye.
Bye-bye.
OK, let's go to an email question this time. Peter Duffy says, this question has been with him for over 40 years. It would be great to get an answer. Question: water is H2O. Hydrogen is highly flammable and oxygen is necessary for fire. Then why doesn't water burn?
OK, yeah, it's a common thing that often gets asked this. People think, well, if you've got two of the chemicals that you need for burning, hydrogen and oxygen, in the same place, surely that should burn. But then you have to ask yourself, well, what actually makes something burn in the first place? The answer is it's a chemical reaction. Hydrogen as a molecule has a lot of energy. Oxygen as a molecule wants to steal electrons from the hydrogen and therefore satisfy its hunger for electrons. When you react the two together, they join up, share out the electrons they've got to make a molecule of H2O, water, satisfying each other's hunger for the thing that it has too much of or too little of. They form this very stable partnership that they're happy with, and therefore they go from two very reactive things to one very unreactive thing. Water. Water's very stable. It's so stable, that's why there's so much of it around. If things are reactive and unstable, you don't see many of them or much of them in the environment. The fact that this planet has something like 1.37 billion cubic kilometres of water washing around in the oceans on board this planet, that tells you that water is a very stable molecule. It's a very stable arrangement for hydrogen and oxygen to be in. The way in which you can get them unstable again is by giving some of the energy that they gave out in making that stable arrangement back into them. In other words, you could pass an electrical current through some water, and this would split the water molecule, the H2O, back into hydrogen, the H, and oxygen, the O. And they each get a partner, so you get O2 and H2 again. And then you can re-react those to release that energy again. And that's how electric cars which use hydrogen fuel cells are seeking to do this. But water on its own is a very stable molecule, therefore doesn't support combustion or other chemical reactions very eagerly, and that's why we use it to put out fires.
All right, good answer, thank you. Mike in Colchester's called in, Dr. Chris. He says he's got his eyes tested recently. Now, he said you'd think that your eyesight would deteriorate with age. However, he was told that his had improved. How did that happen?
It was a mystery. Normally your vision doesn't change dramatically. The eye consists of the cornea, which is the bit on the front of the eyeball that does about 80% of the focusing of the light, so that's just the shape of the front of the eye directing light inwards. It then goes through the pupil and then through the lens, and the lens is a little blob. It's like the size of a Smartie, the sweets that we eat, actually, and that can change its shape by tiny muscles at the edges of the eye pulling or changing the shape of the lens, and by adjusting its shape they can affect its concentrating or its focusing power, and this then directs the light rays that are coming into your eye so that they are focused. They come to a point just on your retina, and the retina is the light sensitive bit at the back of the eye that turns the energy in light into nerve signals that the brain can then decode at the back of your brain, so that that's how you see the world. We're actually seeing the things in front of us at the back of our heads, which is bizarre thing to think about, but that's exactly what's going on. But when the eye goes wrong, it can go wrong in a number of ways, but usually when we need glasses, for example, it's because the focusing system isn't working properly. And in the case of short sight, what happens is that the lens becomes overly thick. The lens is focusing light in front of the retina, so you can see things very close to you because the light doesn't have to be focused. It's already highly focused by the lens, and so therefore it's easy to see things that are close to you. But going further away, where you need the lens to be less strong, it finds it hard to thin itself down, and as a result the light is focused in front of the retina, and then what you actually see on the retina is the light having passed through a point and then begun to spread out again, so it's blurred. If you're long-sighted, the reverse is true. The lens finds it hard to become sufficiently strong or thick enough to focus things that you're looking at close to you, and as a result the light from things close to you ends up being focused behind the retina, so again it's blurred. And as you get older, your lens becomes stiffer anyway. You get a condition called presbyopia, which means it's harder for the lens to change its shape to the extreme. So it finds it very hard to get very strongly focusing for close-up work. It also finds it harder to get very thin for long-distance work. So you have a sort of zone in the middle of your vision where you have good vision, but at the extremes it deteriorates. And that's when you start to need glasses called bifocals, which have lenses of two different strengths. One lens for close-up work and a different type of lens for further away work. Why this person in particular should have a prescription, a lens prescription that's changed, difficult to know. It could have been that something else has happened with his health, which has meant that his general health has improved and he's got his focusing power back up in his eyes, and something was stopping that happening before. It could, heaven forbid, have been a shoddy eye test done previously. Without actually seeing the case and seeing how different the prescription was, it's very hard for me to say.
All right. Let's go skyward now. Leanne has sent an email in, and she says, what makes stars appear in the sky?
Well, NASA estimate that there's something like 10 to the 22 stars in the night sky. So the universe, the known universe, this universe we're in, has 1 followed by 22 zeros, stars in it.
Wow.
And those stars are, some of them, quite similar to our sun. Some of them are much, much bigger. Some of them are much, much smaller. And some of them aren't even there anymore because the light started to leave them so long ago that the stars have since blown themselves to pieces and they don't exist anymore. And what we're seeing is the vestige of the light they gave out still on its way to us. And if you waited long enough, you might eventually see them blow up, because our sun, for example, has a lifetime of about 10 billion years. We're about halfway through our star's lifetime. It's about 5 billion years old. When it gets to the end of its lifetime, it will blow itself to pieces. Now, the stars are out there all over the place, and that means the light that comes to us has been travelling, in some cases, for billions and billions of years. In fact, scientists recently reported seeing the furthest back in time they've ever seen. They were watching light from a star which blew itself up about 12 billion years ago. Now, the universe is only about 14 billion years old, so this was a very young star in a very early universe. So the answer is there are lots of these stars out there, and they're sending light towards us all the time.
Right, and this one, Chris, Dr. Chris, says Ken, please could you tell us why you can't tickle yourself? Good question, yes.
Well, scientists have actually looked at this very question. There was a paper in the journal Current Biology a few years ago, and they did studies on people who were asked to concentrate on a particular part of their body, and they were monitoring what their brain was doing, and then they were tickling that particular part of the body and seeing how this was changing in the brain. And the answer is that when you scratch yourself, your brain detects, because the brain is planning the scratching movement, it also knows which bit of the body it's applying the scratching to. And so it sends a kind of auto-cancellation signal to that part of the brain, telling it to ignore any signals coming from that area or suppress them. And this is probably part of the normal way in which our brain helps us to screen out what's unimportant to us. Because, for instance, none of us, when we're wearing clothes, spends the entire day conscious of the clothes we're wearing, unless we're wearing something particularly uncomfortable, for example, or something that gets your attention for some reason. But unless you consciously think about it, you don't think about the clothes in contact with your skin. But if you had no clothes on and someone ran their hand all over you where your clothes were touching, you would be conscious of it. So there's a system in the brain that cancels out either recurrent or planned stimulation and deducts it or subtracts it from what you're experiencing, because what's important to us is not what's not changing so much as what is new, because we need to focus our attention on what is the unexpected, because it's the unexpected that could catch you out and get you eaten by a predator or burnt in a fire or fall out of a tree or something. So it's part of our self-preservation mechanism, I think.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Now, it's time to open up the phone lines once again, Dr. Chris, and welcome Tony onto the show. Good evening, Tony.
Good evening, my lovely lady.
Oh, how charming of you.
It's very nice.
Now, what's your question for Dr. Chris?
Well, it's a broad question, really, just basically. Fibre optics, they're using computers, don't they? I just wondered roughly how they work.
Yeah, good question, Tony. And if it wasn't for fibre optics, then we probably wouldn't have an internet, because most of the information that travels around the world travels via fibre optics now. The way it works is because of a phenomenon called total internal reflectance. And a fibre optic consists of a certain very high purity kind of glass, which is ensheathed or surrounded by a different kind of glass. And when a light ray goes into the glass, it is reflected off of the junction between the two glass layers at a very shallow angle. And in fact, it's so shallow that when the light tries to bend, when it goes from one type of glass into another, it would have to bend so much as to have come outside of the glass, if you see what I mean. Mm-hmm. So that's a physical impossibility. So the light ray instead is reflected back inside the glass, inside the fibre optic, and that's called total internal reflection. And so as a result, it doesn't matter what the configuration of the fibre optic is, you can bend it, twist it, whatever, the light is always bouncing off at a very shallow angle inside. So if you inject pulses of laser beams into the fibre optic, it will bounce off all of the edges and carry on in a straight line down the fibre optic. And the way fibre optics are used to convey data on the internet, for example, is that you have a laser pointer or something, some kind of laser source at one end, and you turn your data signals into digital pulses of noughts and ones, so light on, light off, almost like Morse code or something, but laser, flashing very fast. The light then goes into the fibre optic, travels at the speed of light down the fibre optic, and then at the other end there's a light-sensitive diode which picks up the flashes of light and turns them back into electrical signals that your computer can understand. And enormous amounts of communication are done this way. It's possible to send huge amounts of data with very little loss of signal or signal degradation, because if you use a wire, of course, you've got resistance in the wire. But if you use light, it's very low resistance, and so you can get things going very long distances with very low loss of data. And people are sending a terabyte, so that's 1,000 gigabytes down these things every second, and it very, very fast and very, very faithful transmission.
Oh, it's lovely. Is broadband part of this?
Well, yes and no, in the sense that what connects the exchanges, for instance, most of the high-speed connections with the big internet router systems are based around fibre optics. But broadband is a thing called ADSL, which is asymmetric digital subscriber lines. And what this is exploiting copper wire between the exchange and your house, and it adds a signal in parallel to your phone signal to the phone line, and that is modulated to carry the internet signal. But certain providers, including I think Virgin now, are providing alternative approaches. I think they're using fibre optics, which, because they can carry the data more quickly and at higher bandwidth, you can get much more data down the fibre optic, so you get very fast download speeds, for example.
They have to put them in, do they? I mean, you know...
Yes, they do, because a fibre optic is a very specialised thing.
Yeah,
you need the fibre optic cable for it to come down. You can't just use normal copper wire, because obviously copper carries electricity, but it doesn't let light go down it.
Thanks, I've learned a lot there, sir.
Thank you very much, Tony.
Thank you.
Now, Chris. Agnes in Braintree says that she spoke to you a while ago about a star that her husband has spotted which appears to jump around. You suggested that Agnes should have a look into it, but she hasn't got round to it, Chris, and she was wondering whether you'd found out any more about this.
I haven't heard of a star that jumps around apart from Tina Turner and Rod Stewart. They're two stars that jump around a lot. But the reason that stars actually twinkle, if perhaps that's what she's thinking of, is because of the different density of the air. When light travels through something, although we tend to think of light as this fastest thing in the universe that travels at a constant speed, it only travels at a constant speed in the same medium. So if you change the density of the thing that light is travelling through, it does change its speed. And when you heat up air in the atmosphere, for example, so you have hot spots and cold spots, when the light goes through a hot spot, it will travel a bit faster, and when it goes through a cold spot, it will slow down. But when it changes speed in this way, the other thing that happens is it bends a little bit. And so when the light comes through the Earth's atmosphere from a distant star, it will get bent all over the place. And as a result, the star appears to move a tiny amount in the sky. And that's what gives it that twinkling appearance. Exactly the same science explains why you see mirages above a hot road. It almost appears like there's a sea of water hovering above the road in the distance. And if you say turn on your toaster, or you look at your bonfire, and you look above the toaster or the bonfire, you see things behind the toaster or the bonfire appearing to shimmer or wiggle. And that's the light speeding up as it goes through the warm air above the bonfire or the toaster, and then slowing down again in the cold air, and it's bending as it does each of those contortions, and as a result it makes the things behind appear to move, because your brain thinks that, well, they must be moving because the light is coming from a different direction, so it's an optical illusion.
Now, we've had a text in here, and it's from Rick heading home from Ely. He says, I've just started hypermiling while driving, much to the annoyance of some. Does Dr. Chris have any tips? What's that about, Chris?
Yeah. Hypermiling is a phenomenon, I think it came to us from America. And this is the practice of trying to squeeze the last tenth of a mile out of every single ounce of petrol that you burn or fuel in your car. Yeah. So in other words, it's people who go for mega economy. They're trying desperately to achieve the highest possible fuel economy that they can. Now, some of the techniques are not necessarily very safe. For instance, a good way to increase your vehicle's economy is to do what the Tour de France bicyclists do. That's to get right up close behind somebody else, because they're doing a lot of work against air resistance, pushing the air in front of a vehicle or their bicycle out of the way. And that means that behind them there is a relative vacuum, and if you sketch yourself into that gap behind the vehicle in front or the bicycle in front, then you're pushing less air out of the way. That means you're doing less work, and the thing that makes your vehicle do work is the fuel. That's where you get the energy to push the air out of the way. So if you do less work, you'll burn less fuel. So that's one thing that people do, and it's very dangerous because, of course, if that vehicle in front stops very quickly, your reaction times at the kinds of speeds that are efficient to drive at like that are going to be insufficiently fast in order to enable you to stop before you slam into the back of somebody. So it's an incredibly dangerous thing to do. In the Tour de France, obviously, there are accidents because of it, but most people are travelling a bit more slowly than a car, so you can normally avoid a pile-up. There are other approaches which are much more sensible, which are that, just to know a bit of physics, which is that the drag force, in other words, the force on the car due to air resistance, varies according to the speed cubed. So in other words, if I double the speed of my car, the amount of work I have to do to push the air out of the way goes up by 2 times 2 times 2. So it's 2 cubed. That means I'm having to do 8 times more work to travel at twice the speed. So if you increase your speed from 40 miles an hour to 80 miles an hour, you will be going twice as fast, but you will burn 8 times more petrol to travel twice as fast. And that's why aeroplanes tend to go at 500 miles an hour. You don't go flying around at the speed of Concorde, because to get to those kind of speeds uses so much fuel that it becomes preclusively expensive. So keeping your speed down is in fact the best way to do this. And I recently had to get a new car because my car's clapped out. And my new car has got, it's a diesel car.
Yeah.
I'm very pleased with it, but it has an instant fuel readout. So I'm able to see exactly what speeds give me the best economy. And I'm pretty gobsmacked to say that I had not realised quite how much more I would be spending by travelling at higher speeds than lower speeds.
Sure.
I think the most efficient speed to travel at is about 55 miles an hour in the highest gear possible, because then the engine is doing the least work in terms of internal losses, because the engine turning itself over has friction and losses. So you need to get the engine revs as low as possible, and you need to get your speed at a reasonable speed to cover the ground, but without maxing out on the air resistance. And so I think 55 miles an hour in the highest gear is said to be the most efficient form of driving.
Good one. Now, Andy's on the M1 and he says, Chris, how can stinging nettles, even when they are very small and in -2, -3 weather, have such a strong sting? Yes, I've noticed that, Andy, as well. I've been gardening.
They're horrible things, aren't they? And they're very clever, actually, because scientists have shown that in areas where stinging nettles are more often grazed by animals, the plants there have developed more prickles, more little needles, and they tend to be more stingy too. So they've kind of learned to defend themselves even better. But the spikes that you see on a stinging nettle plant, resplendent with those lovely hypodermics, those little spikes are made of silica, sand. They're little tiny tubes of glass, if you like, and they're very fragile. And when you go past them, the silica finds it very easy to penetrate the skin and then snap off. And because they're like little straws, they're hollow. And the stinging nettle charges them with a number of molecules, including histamine, which we also make in our own body, which is an inflammatory chemical, and serotonin, that's another one. Serotonin we also make in certain cells, including our blood platelets, and that also makes you sting because it's part of the body's inflammatory system. So the stinging nettles have learned to use our own inflammatory chemicals against us, and they just have a store of those chemicals at the base of these tiny straws, and whenever you snap one off, it pulls some of the chemical out and into you. So it doesn't really matter what the temperature is, as long as it's not so cold that these concentrated molecules are frozen and they can't move into you. But usually you'll find that they sting quite well in the cold, because the silica is even more fragile and it goes into you and then puts these chemicals in, and then you get an inflammation in the area where they're delivered. But it's a sterile inflammation, because all they're doing is fooling your immune system into thinking that something nasty is going on in that area. So then you get the inflammatory cascade in the area, and that's what a stinging nettle bleb is, because the histamine makes your blood vessels open up, makes the blood flow more, and it also makes your blood vessels leaky. So what you get is a red area because there's more blood. It tends to be hot because there's more blood. It tends to be tender because the histamine also winds up nerve fibres in the area and makes them more sensitive. And it also swells up because the increased blood and the leaky blood vessels mean that blood oozes, and the proteins from blood ooze out of the blood vessels into the tissue, making it swell, and that's where you get the little blob.
You got me onto dock leaves now. Why do dock leaves work on stings?
Well, I'm not sure there's actually any evidence, really, that they do. What we think actually goes on is that you're invoking something called the gate theory of pain. This is after Melzack and Wall, who were two scientists in London who studied this. And in the same way that if you bash your head or you bash your hand, the first thing you do is rub it better. And there's very good evidence that when you rub an area, by stimulating nerves that pick up the sensation of rubbing, so gentle, non-painful rubbing, those nerves can switch off pain nerves in the spinal cord. And so by rubbing an area, what you're doing is inhibiting the pain input from that area and switching it off. So the dock leaf is probably not necessary. Just rubbing the stings is probably going to be just as good, actually.
Mike says that he thinks that jet lag is a myth. What do you reckon, Dr. Chris? I think it's very much there.
No, there's very good evidence for jet lag being a reality. And I was talking to someone about this earlier today, actually. It's really fascinating. Scientists in the last few years have identified where in the body clock is, and it's a reality. You have a cluster of a few thousand nerve cells in the base of your brain, a structure called the hypothalamus, and in the hypothalamus is this cluster of nerve cells called the suprachiasmatic nucleus, and it's called that because it sits above your optic nerves, the optic chiasm. And this cluster of nerve cells runs a sort of genetic domino effect where the cells turn on one gene and that gene turns on another gene, which turns on another gene and turns off the first gene. And it goes around in a sort of genetic cycle, taking 24 hours to complete that cycle. And when it turns on these various genes, they alter the activity of the cell that is turning them on. And so this means that these nerve cells increase and decrease their activity periodically, just like a clock ticking. And because they're connected to other bits of the brain, they tell the brain the time. So we have this clock, and it follows about a 24-hour rhythm, and it also produces hormones which go around in the bloodstream and then regulate individual clocks in every single one of the cells in our body. So every cell in our body is able to keep time, and it keeps its time because it follows this central metronome in our brain. And some scientists last year in the journal PNAS published a paper where they took a sample from the skin of patients, and they were able to show these genes turning on and turning off in these skin cells. And what's really intriguing is that they showed if they got skin cells from people who describe themselves as night owls, people who stay up half the night and then get up late, they had a slightly different clock sequence running than if they got skin cells from people who were larks. They got up very early. So the genes amongst these two different types of people are slightly different, and you can see that just by looking at skin cells. So every cell in your body keeps time, but you have a very specialised clock in your brain, which is also set by your eyes, and that keeps the time of all the other cells. And when I say it's set by your eyes, that's the key, because the retina has a special population of ganglion cells at the back of the eye, and they feed into this clock in the brain. And when you're exposed to daylight, this sends a signal to the clock saying, right, it's daylight now, must be morning. And this is how the clock gets set in the first place. And so if you then fool your clock by day not happening when it's expecting it to, the clock is out of whack with what your eyes are telling it, and so all your rhythms are out because you normally coordinate your body's hormonal levels with what time of day it is and therefore how active you are, and that's how animals know to go to sleep at certain times and wake up at certain times. If they go off kilter, it makes you feel very unwell. And there's evidence now that lots and lots of diseases and illnesses are linked to body clocks not working properly. That includes mental illness, and it also includes things like cancers, because doctors have found that if you give drugs for cancers at certain times of the day, they work better than if you give drugs at other times of the day. And it's all down to your body clock.
Does carbon dioxide in fizzy drinks damage the ozone layer, says Kevin in Lowestoft?
Thankfully not directly, but indirectly, potentially, yes. Carbon dioxide can damage the ozone layer because it contributes to global warming, and the warmer the Earth is, the less well we make ozone, and the better that the chemical reactions that destroy ozone occur. So a warmer world is one in which the ozone layer is more in jeopardy, but fizzy drinks use such a tiny amount of carbon dioxide relative to the huge amount there is on Earth already that it's literally a drop in the carbon dioxide ocean. The biggest contributor, in fact, are animals, because physics and other measurements show that we have on Earth about the average person eats about their own body weight in meat every year. It takes about 3 years to fatten up animals for us to eat, and therefore there must be 3 times the weight of humans on Earth in the form of animals being fattened up and eaten. And if you work that out, it comes to about 20% of the carbon dioxide that we make every single year is just due to us growing animals to eat them. And so animals are a massive contributor of CO2 and other greenhouse gases like methane, which come from cows and sheep. And so there's far more important things to worry about in terms of CO2 than fizzy drinks. The average coal-fired power plant in an afternoon will chuck out 3,000 tonnes of carbon dioxide. That's in a few hours. I think even the most prodigious drinker of soft drinks is not going to manage to release or liberate that much carbon dioxide that quickly.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.